Okay, I think we're live. Alright. Spotlight is on. Alright. Thank you all for being here. My name is Verde Arbusto. This is the Schumann Resonance Harmonics channel on Facebook and on YouTube. I think more so on YouTube these days. And I want to thank you all for being here. Thank you for, once again, still the same day that I did the live stream with Alex. And, I figured since I'm already broadcasting and doing stuff, I might as well read through one of these articles that's, kind of a technical thing. This is a little higher order. I think some of you are ready for this. This is something that's, this particular subject is something that needs to get spoken of. First off, my stated clear intention here, the reason for doing this video is I'm working through the discussion about how does the Schumann resonance spectrograph and the spectrogram work. Okay, so this is a big ass topic. I myself am exploring this very thing, and hold on a sec. All right, so I myself am exploring this very issue of what is the Schumann resonance, spectrogram. And hold on a sec. Okay, we're back. All right, so got to make sure the backdrop is all in order. My mom might, if my mom were alive, she would be watching this and she would have said something about the backdrop. So that one will be okay. But that would have drove her crazy, and it would drive me crazy too. All right, so what we're talking about here is, we don't want to do that. We're talking about the spectroscope, spectrogram. How do you read it? What is the signal telling you? And specifically related to the Schumann resonances. And in this particular case, we're talking about something that's really important. I've mentioned this before. It's the horizontals, the dedicated frequency lines. Okay, now, the dedicated frequency lines, those are the ones that are like absolutely flat, straight, as you might say, that are not at, first off, they're not harmonics. They're not at the harmonics point. So we're looking for one of them in particular is the 17, the near 17. It's the 16.7 hertz line. The other one is that broken 25 hertz line. The other is there's a number of like 4 or 5 that are below 10 hertz. There's one at, well, I would say at 11. Okay, so below 12 hertz, I would say. There's 5 or 6 various these here that I'm talking about that's up there on the screen right there. You see that is the difference. This is what the point here of all of this that I bring up with these absolutely flat dedicated frequency lines is that they're a product of something, that it's a telltale kind of sign of where they're resonating, the frequency of what they're resonating at. And it's important to be able to figure out what is happening. If you spend this time looking at the spectrogram and the spectrogram, and looking at it, kind of deducing all kinds of stuff from it, that it's extremely important to know what the lines are, what they represent, and to be able to transcribe, I think would be a good word. Decrypt is another good word. The patterns of the Schumann resonances, the harmonics reports. There's information there, but what are you looking at? All right. So it's important to know before a person starts pulling information from there. What are you looking at? What do you think you see on the Schumann? All right. So I'm going to read this. Onward and upward. All right. So this is, we're now 5 minutes into it, all right. Monitoring mains, power grid amplitude modulated signals. And first off, this is on deltafabri.wordpress.com. All right, link will be in the description. Written by Fabrizio Mansione, May 24th, 2017. All right. It is not easy for me to start this full article as it collects about a couple of years of technical work conducted with other friends. I decided to divide this work into 3 parts. The first part made by Jozef Oksiuta, okay, VK4 EBT from Australia. A second that follows some old work done by Kurt Dietrich from Germany and the hardware used during this test, and the last one where I used the same equipment in my garden collecting signals scattered by amplitude modulation of the 50 Hertz power grid for about a year or more. I also want to thanks D. Hine for his, quote, philosophical, unquote, and lateral contribution that enticed our curiosity to deepen and finally to deny some of his bizarre esoteric theses. As a matter of fact, it has been, scrolling up, it has been a great experience that has led to the realization of other ongoing projects currently underway and under development. All the work done is personal production of the article's authors and refer to them for any form of use of it. All right, well, we'll have to ask them at a point removed from now. I also would like to thank you, Renato Romero, that's a great name, and Cloud Ray for helping me in other investigations which started off from this joint work and will be discussed later. Okay. Moving on. This work was born from a correspondence between me and Kurt Dietrich. I'll get the link in the description. About a signal received in the Val Troncia in November 2013. In parentheses, you can see recording examples of it here, and I have actually taken the to, they give you these, all right. So there's more stuff to this. Okay, I'm not going to get into it, but I've already kind of clicked it and that as well. All right. I was surprised by this type of signal in a desert and quite quiet. That's, she's about to quiet. That's Quiet is quiet. That's quite. All right. Anyway, quite place over the Western Alps, where usually natural signals under 10 hertz are received loud, that should be loud and clear, like then resonances or geomagnetic pulsations. And Alpha, I was just reading up about this the other day. These are resonances that happen higher up. Then, that's a mouthful. Resonances happen way up in the upper ionosphere, whereas Schumann resonances happen in the ionosphere Earth cavity. All right. Or geomagnetic pulsations. I seemed to see in this signal a possible relationship with anything relating to power lines, harmonics, very similar to what is called PLHR, power line harmonic radiation. And I think I looked that up. Yeah, I think I did, yeah. That's something that, oh, good golly, something at some point I could look into. You may or may not ever see that article. Anyway, this was the signal received in 2013 up there. The rest was a result of mere curiosity. Actually, I would be curious. Oh, so this is power line harmonic radiation observed by a spacecraft. Wow. So they can see power line, that's kind of what I'm getting here for power line harmonic radiation from outer space. All right. This is fascinating. All right. Onward and upward with the topic. All right. So this is sort of where we're at here. This is the nuts and bolts. At like 10 minutes into this, this was the nuts and bolts of why I kind of wanted to read this, is because you can see these here, the dancing sine waves. All right. So these are what we might call artifacts, oddballs in our spectrogram. This is a spectrogram, and you see this all. This is, you see this here. This is 2, 4, 6, 8, 10, 12, 14, 16. You see this line here, 16 and a half, 18, 20, 22, 24, 6, 8, 30, 32, 34. So we're getting up close to the time screen. Sure. And so by the just in case it's not obvious, this is not from Tomsk, because it's not from Russia, obviously. This is from Oksiuta, how you ever pronounce it, from Australia, okay? So this is from Australia. For my Aussies out there, head up, word up! Yep. So this is coming from your place. All right, so anyway, you see the resonance here, 4, 6, 8, right, but 8, below 8, this is the Schumann. And then you see this oddball here at 2. Okay, you see that at 2. So at 2. All right. So, Dancing Sine Waves by Jozef, Oksiuta, Australia. All right, so it's in the country of Australia. It is a common observation that sub-50 Hz ELF signals seen on spectrograms appear to have an image that is symmetrical with respect to the 50 Hz spectral line. For example, what appears to be a 2 Hz signal can also be seen mirrored at 98 Hz, which is not here. You don't see that at 98 Hz. This implies the presence of sidebands around the 50 Hz signal, and thus both the 2 Hz and 98 Hz signals may actually result from the 50 Hz mains being amplitude modulated by another signal of 48 Hz frequency, a known phenomena resulting from, e.g., for example, motor slip. Okay. So as a motor is kind of oscillating back and forth in its frequency, back and forth in its operating kind of parameters, the frequency that it's operating at, it changes and it modulates. All right. An easy way to ascertain, An easy way to ascertain whether such signals are indeed carried through the neighborhood by local mains is by simply amplitude-demodulating domestic power supply very much in a similar fashion to the demodulation process in an AM radio. All that's required is a step-down transformer for safety, a full-wave bridge rectifier, and a capacitor to provide some light filtering. The resulting quasi-DC signal, when fed to our spectrum display, should reveal the modulating signal of, as in our example, 48 Hz, thus confirming that the originally observed 2 Hz and 98 Hz signals are fake, and simply the sidebands of amplitude-modulated domestic mains electricity. You can see a general example here. Not there, you see it here. All right. So this is here. If you're following along, this is hertz. That's 32, that's 34, 36, 38, 40, 42, 44, 46, 48, 50. Look at that. Look at how bright that 50 is. All right. All right. So we're just looking at modulated. All right. So even though it was not directly used in this test, with Jan's permission, I put here a prototype of one of his ELF receivers. He has conducted several experiments on the reception of the propagation of the amplitude modulation of the electric lines, that's a mouthful, at his home using, as in our case, one or more Earth dipoles. For more, please visit his website here, and I will put that in the link as well. Alright, so they're giving you schematic of, it's a spectrogram here. Alright. They're picking up electromagnetic signals. Alright, so this is, I'm not sure what I'm looking at, but it's fascinating. Printed circuit board. That's a schematic, and that's the board there. Maybe I'll have that as the thumbnail. I'll take a maybe I'll do a screen capture of that, and I'll have it as a thumbnail. Anyway, all right. Simple ELF direct receiver by Kurt Dietrich, Germany. There are many different ways to receive and record electromagnetic waves in the range between 0 and 50 Hertz. Some amateurs directly connect the sound card of their PC with an appropriate coil and save the received signals with a software sound recorder such as WAVE or MP3. Oh, isn't this fucking fascinating? This method has some disadvantages. The strong 50 Hz mains signal, which are received involuntarily, will overdrive the signal if the amplification exceeds a certain amount. So this method doesn't permit high amplification values, which are sometimes necessary to detect interesting signals of extremely low level. One good reason to use the receiver presented here. All right. Many sound cards, this is, okay, I didn't even know what was in here. All right. Many sound cards show a strong and increasing attenuation from 16 down to 0 Hertz. To build a high-quality ELF receiver, you first should care for an appropriate sound card. Use an external USB sound card with a linear frequency characteristic down to 10 or even lower. If you can't find an appropriate type, you can open the housing of the card and replace the serial input capacitor with a bigger one. Okay. The second step to reach the goal consists in using the right recording software. For programmers who are familiar with the question how to access the corresponding software devices in their PC, this may be an interesting challenge, but I recommend a more simple way by using freely available software, Spectrum Lab. Giving you the spectre there, what do you call it? Not the spectrogram, it's the schematic. Thank you. All right. So he says, now we can care about the receiver circuit itself. It consists of 6 single operational amps of the type OP07, which have a very low offset voltage, which is essential at high gain amplifications. In the circuit diagram, you see a one-to-one input transformer with a lower cutoff frequency under 1 Hz. This expensive device, available at Jensen USA, is only needed when you intend to use the receiver with Earth probes. See end of the article. If you only use a coil, you can omit this device and connect the coil directly to the 100K serial input resistor. After a pre-low-pass filtering and pre-amplifying in the first op-amp stage, the gain is increased by an inverting amplifier. The amplification can be calculated by dividing the input-output resistor by the pre-resistor. With the switch S1, you can set the gain at this stage between approximately 5 to 50. The 3 next op-amps are working together as sullen key low-pass filter with a cutoff frequency of 21 Hz. All signals above this value are attenuated with a 36 decibel per octave. Attenuated 36 decibel per octave. A relatively good value which cares for suppressing even strong mains hums to a non-harmful level. After the filtering stage, there is a high-pass filter which eliminates an eventual offset created by the previous stages. As the cutoff frequency is extremely low, it will not influence the received spectrum. The following op-amp works as amplifier and adding stage at the same time. By P2, the first amplification can be adapted to the following system, PC. When P1, the offset have corrected to 0 if necessary, to set to another value if required by the following stage. If you want to protect the following sound card against high voltages, you may add 2 diodes as shown in the diagram. Optional. The type power supply you can use depends on your own environment situation. If you use a set of rechargeable batteries, 4 or 5 times 1.2 volt in series, I recommend the SIM0512D power chip that converts a 5 volt input voltage, 5V, input voltage to a voltage of 2 times 12V, which is needed to feed the op-amps. If the input voltage is higher than 5V, you can use the 7805 voltage stabilizer chip at the input, optional. You also can connect metal sticks or probes at the input. This requires the input transformer mentioned above for safety reasons, vagabonding currents. The receiver and the PC connected to it must be completely electrically isolated against the ground where you put the poles in. If you use the poles in a distance of 1 to 5 meters, you can receive the same and sometimes also different signals in the coil. All right. That's a pretty cool diagram. Oh, look at that. Fun. All right. Okay, gallery at 24 minutes. All right, so I'm just going through some of this stuff. What do we want to read here? Oh, that's interesting. Scrolling down here, I'm just seeing what's this. What's here? That's interesting. That's our frequencies here, hertz, right? That's 10. What are we looking at? 2, there's 4, 6, 8. And there's interesting patterns there. And this is a different spectral, obviously. 50, that's a 50 hertz line there. That's 100 hertz, okay. Then you see 10, 15, 16. See that? 16 and a half, almost 17. That's the one there. And then at 10, see another one there. 80, it's 85, you see one there. Okay, and then 110, 120. Okay, so there's just interesting notes on what you're seeing here. 50 again, all right. Oh, that's interesting. All right, so I'm not reading through this article. About 25 minutes, and I think I'm going to do another video of just this. Wow. Yeah, I'm gonna. I think make this a two-part. This is 20. I'm at 25 minutes in this already, and I don't want to make this that much longer. All right, so. And I may or may not make another video of it. I think this is, I've said a lot there so far, but this is interesting. This would make its own video. Honestly, God, there's a lot of stuff in here. I like the idea of 10-minute videos, and this is now almost into the old 33.11 range that it was at. All right, so thank you all for being here. I appreciate everyone. Hold on. There we go. Thank you, everyone, for being here. I appreciate your love and support. I love this graphic here. This is just the coolest. This is just cool. So I'm going to make this going to do a capture of that and make that the thumbnail for that video, if and when I make it. Things don't always work out to how I plan them. Anyway, thank you all for being here today. I appreciate your love and support and for coming around and helping me and just being part of what's happening. This is I am not here representing the status quo. There's not another way to put it. I volunteered to come here to help people at this time, and it's largely what my job is. And not everyone is ready for what's happening, and not everyone is ready for what their part in it is. And those who are ready for their calling, I call you the crew. And there's a few of you that are that have shown up for duty, as it were, that are here for kind of the long haul. And there's a few of you that I know watch the videos all the way to the end, and I appreciate it. This is. I try to make this as fun and interesting as I can, but a lot of this stuff really is very mentally draining, and just trying to figure it out, and let alone figure out where it fits in and how it fits in. It's some pretty intense stuff, So I do it in part for you guys, for you all, because I know that if it's something that perks my interest, it's because my guides have said, it's time for this lesson, and that, like I said, this video is about, and the last few of them have been about the spectrographs in general, spectrograms, getting to know those, but even more specifically, how does the Schumann one work? And we're getting closer to the electromagnetic, how to read the electromagnetic spectrum on, the spectrograph. The spectrograph is a thing that puts it down. The scope measures it. The graph writes it out, and the gram is a thing that you get as a result of it. It's like conjugating the signal of the spectrum, the spectroscope, spectrograph, spectrogram. All right, there you go. That's the three stages of the three dimensions of the spectra, is getting the signal and then processing it and then spitting it out to where you can understand it. All right, so onward and upward. Do we got any music? No, I don't play. Can't play. Oh yeah, actually, I think I can. I get sound card. Let's see. Can I play anything here? Let's see if I can get this for Bradley. Holy fuck, that's loud.
I don't believe you're ready for this.
I don't believe you're ready for this. All right. So, actually, I don't normally do this, but I think this would be a good idea. I'm going to show this. Updating this. Where are you at? Right here. All right. So if you're still listening, I want to end every show with a view of the Schumann somehow. So this is the one from disclosurenews.com. Disclosurenews.it. So if you've never been there, you get that. Right. So you click on it, you get that. And then down here, they have these. And then they have these. All right, this is the history. Yeah, if you're feeling the beat, go on over there. All right, this is to give them the amplitude mag values, tell us how you feel, how to read the graphs. All right, so we're now at 32 minutes. So thank you all for being here. I appreciate your love and support.